Hey guys, what's up? Welcome to this short little video series on the Diamond-Mortensen-Pizzarides model. In this video, we're just going to give an overview of the DMP model. Let's go. So the plan for this video is as follows. I'm going to provide a brief background on the model's creation. I'm going to introduce the DMP model, and I'm going to then show the derivation of some key equilibrium conditions, that being the job creation condition, the Beveridge curve, and the wage determination equation. In the following videos, we'll be drawing some pictures and do some more comparative statics. So what is the DMP model? The DMP model is a workhorse of matching models, which was developed by Peter Diamond, Dale Mortensen, and Christopher Pizzarides, hence the acronym DMP. In 2010, the authors received a Nobel Prize for this work. This model is unique in the sense that it is the first model to express a fully defined equilibrium unemployment theory considering the perspective of both firms and workers. So the setup is as following. We have to define our environment for workers. There's a large fixed labor force of measure 1. We can think of workers as being points along the interval of 0 and 1. So our employed worker plus our unemployed worker sums to 1. Our environment for firms is that firms post vacancies at a cost of CY per vacancy, and the measure of vacancies in our economy is defined by V. Each firm has only one job to fill if they are vacant. And our vacancy rate is defined as follows, where we have V, which is the number of vacant jobs, all over the total number of jobs in the economy, which is the vacant jobs plus the filled jobs, or the mass of employed workers. In terms of matching, each match produces output Y. Matches are formed through a stochastic process and produced by a CRS matching function, MUV. Labor market tightness is defined by this theta term here, which is V all over U. Some additional information that you should know is that time is continuous. So this is going to affect the way our Bellman equations go and look, with a little r in front of each term on our left-hand side. Jobs will be destroyed at an exogenous rate of delta. Wages are determined through Nash bargaining, which is just a way for optimal surplus splitting among firms and workers. And the matching rate for a firm filling a vacancy is defined as Q theta, which is equal to the matching function all over V. And the derivative of this function is less than 0. The matching rate for the unemployed worker is defined by P theta, which is equal to MUV all over U. And this is the same thing as theta times Q theta, right? So we see a relationship between these two matching rates, and P prime, right? If you were to take the derivative of this matching rate with respect to our market tightness, that's going to be positive. So there are 6 equations of this model. We have a vacant firm Bellman, a working firm Bellman, an unemployed worker Bellman, a employed worker Bellman, a unemployed law of motion, and a Nash bargaining condition, where the betas here are our bargaining weights. It should be noted that you should be able to read these Bellmans as a story, where we go and we have the first terms here, right? The ones that don't have this sort of transition value. If you watched my series on applications of dynamic programming to economics, this would be, our discount factor. Everything before our discount factor, that would be called our state, like what's happening now. And our transition value would be what happens, at this point here, where we go and we have this sort of discount factor, right? This could be either a job finding rate, a job destruction rate, and that's really what goes and gives us the full story about what's happening now and what happens later. So we have to keep that in mind for understanding why we're using this Bellman approach. So for deriving the job creation condition, we note the following. We go and we have our firm's story. We have to start from there. Then we're going to note in equilibrium, the value of our vacant firm is going to be equal to 0. That's what we go and we have here. Step number 3 is that once we have this equilibrated sort of Bellmans here, we're going to go and solve each equation for J. And once we have that, we can now go and solve for our job creation condition here, which is this equation in the bottom down here. Now we're going to derive our second, equilibrium sort of condition, which is the Beveridge curve. we know our unemployed law of motion equation is defined as follows. We know in equilibrium that the law of motion is equal to zero. That means nothing's changing. That's really what equilibrium is. And from there, we can go and solve for the Beveridge curve, which is just solving for u, and we get the following result. So in terms of deriving the wage determination equation, we're going to first take the first order condition of that there. Step number 2 is that we're going to go and abuse this equilibrium condition of V being equal to 0, the value of a vacant firm being equal to 0, because there are no vacancies in this equilibrium there. Step number 3 is that we're going to note the way we define J in equilibrium from our unemployed firm and what W omega is. So we have to go back to our employed workers story, and we have to go and think about what exactly is W omega there, right? What is our workers' value? And you have to go and rearrange that because we're operating in continuous time. So with this here and a little bit more math, we go down to step number 4, which is solving for omega, which is our wage, and this gives us our wage determination equation. So this is really, a 6.5-minute video covering the entirety of the DMP model. In the next video, we're going to go through some comparative statics and some other stuff with the charts. I'll see you then. Take care.